In this HVAC training video, we're going over if you should replace a thermostatic expansion valve with a piston orifice on an air conditioning system. So we're going over how much work's involved, what the pitfalls are, the positives and negatives, and how easy or not it is to check the refrigerant charge. First of all, how do you know that the thermostatic expansion valve is the problem? So if you know that you have good airflow across that indoor coil, and you have measured the refrigerant charge, and you are measuring a low side saturated temperature on this large line that is very low, say it's below 32 degrees, yet the line temperature on this vapor line is very high. It may be even the same temperature it is in the house or in the building. So maybe this is 70 degrees as a line temperature right here, and the saturated temperature, which is the pressure converted to the, in this case, R410A saturated temperature, is below 32 degrees, then you know you have high superheat. So in this example, we have 70 degrees as a line temp minus 30 degrees as the saturated temperature, and we're left with 40 degrees of superheat. Well, we know that the thermostatic expansion valve should be holding that superheat at somewhere right around, say, 8 to 12 degrees. And so the fact that our coil is starting to freeze, at least down on the lower sections down here, because you have a saturated temperature that's lower than the temperature that water freezes at, yet you have a very high line temperature. That means that you don't have a lot of refrigerant entering into this coil in order to absorb the heat in the air crossing across this indoor coil. You can also look on the high side gauge. So in this instance, we have an R410A saturated temperature of 100 degrees, and so we have a line temperature over here of 90 degrees. So we would take 100 degrees minus 90 degrees as our line temperature, and we have a subcooling of 10 degrees. And 10 degrees is a pretty normal subcooling. So we know that we're not necessarily low on refrigerant charge, but that we have some type of liquid line restriction problem. And so that problem could be a clogged filter dryer, it could be a clogged strainer screen right here, right before the inlet of the TXV. It could be the TXV itself. Now what you can do is you can take this bulb off and you can put it in hot water in order to see if the TXV allows more refrigerant in and increases the low side saturated temperature. So if it does not, then you know that the TXV has lost all of its bulb charge on the top of its head, and that's the problem. If you do put this bulb in hot water, it's going to hopefully open up the TXV a little bit more in order to allow more refrigerant in, and if you do that, the issue is that means that the TXV is the mechanism that is not allowing enough refrigerant into the coil, so you should just go ahead and replace the TXV. Now, in the past, these heads right here have been pretty rusty, and so they were made out of just steel. And so you have a low temperature in here, and you have like condensed water coming on this steel head, and we've leaked refrigerant out of the opening force, which the bulb is the opening force on a TXV to allow refrigerant into the coil. And so nowadays we have a stainless steel head typically right here. So we don't tend to have that problem. We also have a curlicue on the TXV bulb. So this little curlicue right here helps the line from, say, kinking or cracking right here when the installer is putting this together. You could leak refrigerant out of the bulb itself, but a lot of the new TXVs have a stainless steel head on them, so we don't tend to have that problem. And once again, we have the little curlicue. So the first thing is, how hard is it to replace a thermostatic expansion valve with a new TXV? And it's actually the same amount of work regardless of whether you're replacing the bad TXV with a piston or a new TXV. So if you have a reciprocating compressor, you can pump the refrigerant down into the outdoor unit. If you have a scroll compressor, what I would suggest that you do is that you just shut the outdoor service valve lines. So you shut the service valves with the power off. Now we don't pump down a scroll compressor all the way down to say 10 or 5 or 0 PSI, because you could end up having problems where the compressor will be shorting out inside. So we don't do that. So you would only be doing that on reciprocating compressors. And then you're just going to recover the refrigerant out of the line set, which is connecting the outdoor unit to the indoor unit, and you're also recovering the refrigerant out of this coil. You're weighing it so you know how much to, say, start with back in again when you do a pressure test and then a vacuum, and then you're breaking the vacuum with the same amount of refrigerant that you recovered out of the system, and then you would check the refrigerant charge afterwards. The other thing is you could just recover all the refrigerant out of the whole system in order to do this, but I think it's just a little bit easier if you just go ahead and shut the liquid line service valve and the vapor line service valve, and then recover the refrigerant out of the system there. After you've recovered the refrigerant out of the system and the system's at 0 PSI, we can go ahead and switch out our TXV for a new one. Now, what does this get you? So instead of just replacing this with the piston, which is what I'm going to do next, what does it get you to have a new thermostatic expansion valve here? So the big thing about this is a TXV is able to hold the superheat, and what that really means is that the majority of this coil is going to be filled with saturated refrigerant, and that means that you're doing a phase change. So say 80% of this is liquid refrigerant and 20% is vapor, and then over here it's say 50% liquid, 50% vapor, and it's holding the temperature of the refrigerant steady as it's flowing through here. And let's just say it's 38 degrees. As this is flowing through here, it's 38 degrees, and then up here, it's say 75% vapor, 25% liquid, and then all the way by the time it gets up to here, maybe it's 100% vapor. And it's still now at 38 degrees, but now it can increase in temperature. And so maybe by the time it comes out of here, it's 48 degrees. And so the long and short of it is this TXV is going to hold that superheat steady as long as you have proper airflow going across here and the proper refrigerant charge. And this is operating correctly, and there's no clog, say, in the filter dryer before this or in the strainer screen or anything like that. And so if you're turning this system on for the first time, a TXV is going to allow a lot of refrigerant into this coil to absorb the heat from the air crossing it. The thing with a piston is that the times when you need it the most to allow more refrigerant into the system, it's not. It's actually going to end up allowing less refrigerant into this coil when it's high temperature and a high heat load inside the building. And so I'll explain that after we go ahead and replace this TXV with the piston. Now the other thing with a TXV, what's nice is when we go ahead and after we pressure test, after we release that nitrogen pressure, we vacuum the system down and we're breaking the vacuum with refrigerant from the bottle. We open those service valves up, right, and we're getting ready to start this system up and check the refrigerant charge. We're going to be checking that refrigerant charge with the subco method, which is very easy, you know. So you're just taking the saturated temperature on the liquid line. So say it is maybe 105 degrees saturated temperature, and then we're also measuring on the line over at the outdoor unit, and so say that is 95 degrees there. And so you got 105 minus 95, we got 10 degrees of subcooling, so we're accurately charged. But then we also want to measure the superheat to make sure that the TXV is doing its job properly. And so if we were to measure, say, our vapor pressure and convert it to saturated temperature, say we measure 40 degrees, and then our line temperature is maybe 51 degrees. So 51 degree line temperature minus a 40 degree saturated temperature, and we're left with 11 degrees of superheat. So we know that we're absorbing a good amount of heat from the inside of the building in order to lower the temperature. Now with a piston, the superheat is going to fluctuate based on the operating conditions. So you may have 26 degrees of superheat, and that may mean that you have this much of the coil as just a vapor, and as a vapor is flowing through here, it's not going to be able to absorb much heat from the air crossing the coil, and that means that the saturated refrigerant is only doing its phase change here, where it's maybe at 38 or 40 or 42 degrees. So the TXV allows you to have a more electrically efficient operating system. It allows you to pull the temperature down faster. It allows you to check the refrigerant charge using the subcoing method. You don't have to try to determine what the target superheat is. It's going to be able to be very easy for you to be able to adjust the refrigerant charge level. And if there's slightly high or slightly low airflow, the TXV will adjust a little bit in reference to being able to hold that superheat steady. Now, of course, if you have a very restricted airflow, like less than say 325 CFMs or something like that, less than 350 CFMs, the TXV is not going to be able to close down enough. So in those situations, yeah, you know, you're going to have to address the airflow problems. But a piston has no way of controlling the superheat on a system. So the other thing is, if you do have slightly low airflow, the TXV is still going to try to hold the superheat steady, which means that you're going to have vapor refrigerant exiting this coil. And so if you had slightly low airflow with a piston, you're going to end up having liquid slugging at the compressor, meaning that there may be no superheat at that point, and so it's still saturated as the refrigerant's exiting this coil, and so you're going to have both liquid and vapor entering into that vapor compressor, and it's going to damage it. So there's a lot of benefits with using a TXV, and the thing is, it doesn't take that much longer in reference to replacing it, because you also still have to tighten this up anyway. So you're going to have to seal this, and so if you had instead of a flare here, you had a braze connection. Basically, you're going to be unbrazing this external equalizer line out of the tubing, and then while this is still hot, you are inserting your new external equalizer tubing, and that should seal it in. And if you just need a drop of braze in order to help seal it, then you can do that as well. You just want to make sure to not add too much braze in order to then end up clogging this tubing right here. But you're going to have to braze that shut if you were to put a piston in. So let's go ahead and replace this TXV with a piston. Before just trying to replace this TXV with just a piston, you're going to have to determine what size piston is needed for this indoor evaporator coil. And so there used to be on the old R22 systems and older R410A systems, there used to be a piston sizing chart on the underside or on the back of the outdoor unit shroud. But that's not the case anymore, and that's because manufacturers want you to just install TXV. So you may have a very hard time finding the size piston that you need for the system in order for it to even operate okay. And so if it's an older system, you most likely can find that data, and so you're going to have maybe a 065 or 073 or 084 or something like that, and it's going to be a bigger hole size the bigger the outdoor unit size is. And so we need to place this piston into that chamber after we remove this TXV. Now this little Teflon seal, that needs to be face downwards. If you don't have this type of a piston, but you have the older style that do not have the Teflon ring, they typically can get put in either direction. But let's just go ahead and set this down in there, and you see that it won't fit because of the ring. I like to just stick a little piece of copper in there and kind of pull it out. So you see we have a Teflon ring here, we have a Teflon ring here. You're going to want to pull one of the two off, and actually you want to just replace that Teflon ring with a new one. And so let's just go ahead and do that. A lot of times they're squished down, and so they won't seal up very well. Make sure it's fully in there. You're going to notice that this liquid line is a lot lower now. And so this has to get bent upwards in order to kind of meet back up at this hole where it was before. Now a lot of technicians end up saying that this is easy, meaning like the piston is just a lot easier than a TXV, but I really think that that has to do with not being able to be confident in the diagnosis of a TXV or even what a TXV does, like what its job is. And I think that's really where this stems from. But a lot of technicians are going around and doing just this, and then they're bending this up in order to get the system back up and running. But there's multiple issues with this, which we're going to go over in a couple minutes. The other thing is you can go ahead and take a little bit of nylon, because now you have a brass cap and a brass fitting, and so you're going to need something there to act as a gasketing material. And so when it's copper flare, the copper actually acts as the gasket. So a lot of technicians don't know that, but that's actually what is happening. But this is actually beveled, so it has that same angle on the inside, even though it doesn't necessarily look like that on the outside. And so we can go ahead and snug that down. Now if this was just a line, you'd end up pinching that off and then just brazing the end of that shut. Even though this is a long adjustable wrench, I'm going to hold it a little closer to just act as if it's a smaller wrench. Now once again, we're going to leak test. So we want to check right here to see if there's any leaks here or if there's a leak right here, in which case we'd have to let the nitrogen pressure out and find out what the problem is. It could be that the cap itself is not good. You might want to replace that with another one. Once again, if you just have a external equalizer line that's brazed in here, you're going to need to braze that shut and just leak test down here with the bubble leak detector. And after you break the vacuum with refrigerant from the bottle, you're then going to have to check the refrigerant charge with the total superheat method, because you really need to make sure that you're not accidentally overcharging this system with refrigerant, because if that's the case, you're going to end up having liquid refrigerant coming through here and going to the vapor compressor, and it's just going to kill it. Now, it may take a while, so you may think that you did a good job, and hey, this coil is cold, right? It's absorbing heat from the air, the customer's happy. But guess what? Maybe a year down the road, because you're slugging the compressor maybe a little bit at a time, it's going to end up breaking, and that's the problem. So you don't want to just measure the vapor pressure and convert that to saturated temperature and think that you're good if if you have a low temperature like 36 or 44 or 40 degrees. You need to check it with the total superheat method, which means you need to determine what the target superheat is. So you need the indoor wet bulb temperature in the return duct, and you need the outdoor dry bulb temperature outside. You're going to line them up on a target superheat chart. So in this example, you would take, say, 80 degrees as the outdoor dry bulb temperature, and you take an indoor wet bulb temperature, maybe at 70 degrees, and you're left with a target superheat of 25 degrees. Is 25 degrees more efficient than, say, 8 to 12 degrees with a TXV? No, it's not. And so on a day when you need your air conditioning to run, it's going to operate with less refrigerant in this coil. Now, some days it might be down at 19 degrees as your target superheat. And so if it's an outdoor dry bulb temperature of, say, 85 degrees and an indoor wet bulb temperature of 68 degrees, you're left with a target of 19 degrees. Now, that target is actually what's happening in this system, so you need to adjust the refrigerant charge accordingly. If you are measuring a high superheat, as you add refrigerant into the large vapor line out at the outdoor unit, what's going to happen is your superheat is going to lessen, in real time, and it's going to align to your target superheat chart. And so you just want to make sure to not overcharge it by having too low of a superheat compared to what your target is. So a piston is going to wildly differ in the amount of superheat in this coil. Some days you'll have a superheat that's very close, like very comparable to a TXV, and other days when you really need it the most, you're going to have a lot of superheat and not a lot of saturated refrigerant. So it's going to take a lot longer for that building to lower in temperature. The other thing is you're going to draw less humidity out of that building. However, you're going to run for a longer period of time. So it's just the amount of time you might be able to overcome the humidity, but you may have a delta T across that indoor unit of maybe 15 degrees. And so it may not feel like very low temperature air coming out of the registers. And that's just because you don't have a lot of refrigerant flowing through this indoor coil. So is this piston easier to understand as far as how it works and simpler? Yeah, it's just a little hole. The refrigerant enters a little hole, and then low pressure refrigerant comes out. It's very simple. So it is simpler than the TXV. But people are afraid of the TXV because they don't understand how it works. We've got tons of videos on the thermostatic expansion valve, and we have a lot of other resources there. Now, the other thing is the head on the TXV. There's been a lot of advances with thermostatic expansion valves, and so they really don't have many problems nowadays. So we have a stainless steel bulb, we got stainless steel cap tube, we got a stainless steel head, so there's not any rusting. And the stainless steel holds up much better than the copper. And so it's less rubbing, less leaks on the opening force of the TXV head, and this is just a lot more electrically efficient for the system. It's able to reduce the humidity a lot faster inside the building, and so overall it's going to be a lot more efficient, and it's going to help safeguard the compressor by only having vapor exit this evaporator coil to a point, right? If we have too low of airflow, it's not going to be able to do that anymore. But if you don't understand how the thermostatic expansion valve works, you need to check out some of the resources that we have down in the description section below. The other thing is, with some of these newer systems, you're not even going to know the piston size because the manufacturers are not even posting that anymore, because they definitely do not want you taking the TXV out and just putting the piston in. Now, before we replace the TXV, we need to know that we can make our connections back here. So this is a piston chamber right here. And so you can actually just disconnect right here and disconnect right here, and we can put our new thermostatic expansion valve in. Now the issue is we want to make sure that this TXV has the proper size ratings for the outdoor unit. So in this case, this is rated from 18,000 to 36,000 BTUs, and the outdoor unit is actually a 30,000 BTU unit. So this TXV is within the range in order to hold the superheat steady across this coil, which means that you're going to be holding the amount of saturated refrigerant across this coil steady, and that's the secret to this whole thing occurring. And so it's going to allow the correct amount in. And you also want to make sure that this is rated for the refrigerant that is in this system. So in this case, this TXV is stamped with R410A. And if the TXV isn't stamped with the refrigerant or the size, you can look up the model number, and sometimes there's a scan code to just be able to look it up online in order to check out its ratings. There's different style TXVs, and so their connections may differ. So this is made for a different style of a chamber right here, and this one is just braze connections right here and over on the other side. And then this one is a chatlift chamber right here, and then it's braze on the other side, or sweat. So you want to pick out the right TXV for the right job. Now that we have a TXV that matches the size and refrigerant for the system, we can go ahead and replace that along with the install kit. So that should come with Teflon rings for right here and right here. And you can get TXVs that cover a range, and they also have different fittings on the end, so it's almost like a rescue TXV that you could utilize in these systems. And say you didn't have the right size piston, you would end up having to order that from the distributor, and by that time you could have got a TXV. And so don't be afraid of these. You want to make sure to be aware of how they work, how to diagnose them, how to troubleshoot them. And so if you want to learn more about TXVs and air conditioning in general, make sure to check out our refrigerant charging and service procedures for air conditioning book. We also have a 1,000-question workbook, and we also have quick reference cards. And those are all available at acservicetech.com and also on Amazon. Hope you enjoyed yourself, and we'll see you next time at AC Service Tech channel.